everybody. I'm Lennon. I'm based in Liverpool in the northwest of England. And today, Amelia asked me if I would have a chat with you about some of the most interesting facts to me. So that's what I'm going to try and do. Now, I really love mathematics. I like physics. I love science. So I think, particularly today, a lot of people get confused between what a fact is and what an opinion is. And we have this idea of something called fake news, which is quite worrying. And so I'd like to talk a little bit about science and how the scientific method works, because that really underpins our understanding of everything around us, every aspect of science in the world. So the scientific method is kind of an interesting thing. And, I'm not a scientist, I'm an engineer. So you'll have to bear with me in my understanding of this. But essentially what it is that you come up with an idea of how things might be, of something that might be true. And it's very important that you can disprove that idea. If you can't disprove something, you can't know it's true. It's very important to the scientific method. So you come up with an idea which you can disprove, and this is your hypothesis. So you hypothesize that something is the case, like maybe the Earth goes around the sun as opposed to the sun going around the Earth. And then you come up with ways to test that your hypothesis is correct. And ideally, you have lots of different kinds of ways of doing this testing, because the more tests that you can do on a hypothesis, then the more confident that you can be that you're correct in your hypothesis. Now, of course, as you're testing, if something disproves your hypothesis, well, it's not true. And you think, oh, okay, I need to come up with a different idea because that idea I have proven is not true with my testing. And that's basically science. We come up with ideas, we try really, really hard to show that they're wrong, strangely. And then when we can't show that they're wrong, we can have a lot of confidence that those ideas are correct. So that's the basics of the scientific method. And there's a couple of other things that this sort of leads into, which I really am very interested in, have always been interested in. And one is to do with the very big, which is stars and the cosmos and universes and how everything works at a massive scale. And the other thing is the very small. And that's to do with the insides of molecules and atoms and how they stick together and how everything that exists in the world today exists, how it is put together. So up at the very big scale, we have something called relativistic physics, which is an idea of how we can travel long distances and how as you go faster and faster and faster, and you get closer and closer and closer to the speed of light, time slows down for you, which sounds crazy, doesn't it? And it's quite important here to understand as well that we're not sort of imagining this kind of idea. The science tells us that time slows down, which is weird. So, for example, if you have, there's a classic thought experiment that people can do where you say, okay, so I've got two twins, identical twins, born at the same time. Well, obviously not, but let's imagine that. Born at the same time. And one of them goes up into a spaceship and they travel a long way, really far away to the nearest star. And as they travel and they come back and they're traveling at a massive fraction of the speed of light, really, really quickly. Now, we can't actually do that. We don't have technology to do that today, but this is a thought experiment. Now, the other twin, they stay on the Earth and they just kind of live their life and they do their thing, And at the end of this experiment, the twin that has been away traveling really, really fast comes back to Earth. And what the science of this tells us is that the twin that's been traveling really, really fast will be younger than the twin that has stayed on Earth. Not as much time will have passed for that twin. which is a really, I mean, for me, that's a really hard thing to get my head around and to try to understand. So that's an example of why I think relativistic physics is really, really interesting. And there's a lot of sci-fi science fiction books out there that talk about the implications of what these things mean, this time dilation effect. And then on to the physics of the really, really small. And this is often characterized as quantum theory, quantum mechanics we hear about, and we're hearing more and more about that today. There's a lot of really interesting and strange things that are to do with quantum mechanics. And one of the core aspects of this is that everything at a very, very small scale is all probability. It may be there, it may not be there. So there's nothing definite, which is, again, it's kind of, you think, can that be right? I mean, I feel pretty definite that my hand is here, you know. Yeah, it's definitely here. But actually, the science tells us that when you get down to a tiny, tiny, tiny little scale, it's all probability, and it's all things popping into existence and popping out of existence, which is kind of weird. So one thing which is really strange, which I find hard to grasp about quantum theory, is that when you try to measure things at a really small scale, you have a problem, because there is a theory, or principle rather, Heisenberg's uncertainty principle, which says that when you try and measure a thing, you can be very accurate in measuring where it is, its position, or you can be very accurate in measuring how fast it's going and where it's going, its momentum, its velocity. But you can't measure both very accurately, which is another kind of weird thing, because you think, well, why not? What's the problem here? And what's really important, again, is what the science tells us, is that this is not because I don't have a good enough microscope. This is not because my tools aren't good enough. You know, I could make my tools better and better and better. I would never, ever be able to get an accurate value for both the position and momentum of a tiny, tiny, tiny little object, because the universe doesn't work like that, which is kind of mind-blowing. Really? The universe doesn't, I can't do that? Yeah, that's what the science tells us. How can that be? So that's the uncertainty principle of knowing things about tiny, tiny little things. And then I think probably in the time that we've got, there's one other, well, there's a couple of other things actually to do with quantum mechanics I'd like to talk about. One is quantum superposition, and one is quantum teleportation, which is based on quantum entanglement. You know, you've got to look at all this stuff up. But so basically, if we look at quantum superposition, big long word, what does that mean? Well, simply put, when I'm doing maths, right, and I'm adding things together, so I get a number, we'll call that like A, and I get another number, we'll call that B, and it's A plus B equals C. Okay, so if A is 1 and B is 2, then 1 plus 2 is 3. Okay, that's fine. And that's classical. That's the classical way of doing things. That's a classical way. That's how computers work. Every computer, however complicated it is, when you're playing Minecraft or Rec Room or whatever, Call of Duty, whatever it might be, they're basically just adding up lots and lots and lots of numbers incredibly fast. And they do it essentially one by one. So 1 plus 1 plus 1 plus 1 plus 1. A quantum superposition is another kind of crazy scientific idea, which is that instead of having one number for A and one number for B, I can load an infinite number of numbers into A and an infinite number of numbers into B, and I can add them all together to have an infinite number of numbers in C as my output, which is like really hard to understand. But essentially what it means is that instead of my computer having to go 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9, 10, 11, 12, for certain kinds of mathematical operations, my quantum computer can do things incredibly fast. Now, we can't do everything incredibly fast. There are always limitations. There are some limitations to this. but it can do this incredibly fast. So that's intriguing to me. And we actually are building quantum computers today. Google have them, IBM have them, other people have them. You can go online and you can learn how to program them and run your code on quantum computers today, which blows my mind. I'm running out of time a little bit, but I'll be really quick with the last thing, which is quantum teleportation. Now, relativistic physics tells us that nothing can travel faster than the speed of light. That's the upper bound, and that's because time slows down for you as you go faster and faster and faster. But quantum teleportation is this kind of crazy thing where what we can do is we can get a little bit of stuff, a tiny little bit of stuff, and another tiny little bit of stuff at a quantum level, and we can mash them together so they're kind of entangled, so they're sort of connected with each other. And then we can take them apart. We take them really, really, really far apart. And we can make a change to one of them. Boom. And instantaneously, that change will happen to the other one, faster than the speed of light, which is crazy. And that idea is essentially the idea that you can teleport the state of one of these things to the other of these things incredibly instantaneously, basically. Now, I don't really understand that. I'm not sure how many people really understand that, but it's kind of mind-blowing, isn't it? So these are all aspects of why, science is for me like completely amazing and utterly cool and wonderful. And I'm way over my 10 minutes, so I better stop there and have a lovely day.